very warm welcome to all the participants for this webinar organized by Space Education and Research Foundation. As you all know, this is the fourth talk in this series. We already had 3 presentations in last 3 days, and today's topic is future challenges in atmospheric measurements. And this is a very important topic that we have, and for this we have Dr. Lokesh Kumar Sahu of Physical Research Laboratory, Ahmedabad, who is going to speak to us on this topic. And let me give you a very brief introduction of Dr. Sahu. Dr. Sahu did his PhD from Physical Research Laboratory in 2005, and after that he worked in the Indian Institute of Tropical Meteorology, which is called IITM at Pune. And but while working there, he got a very prestigious fellowship of Japan, that is Fellowship of Japan Society for Promotion of Science, and he was given a very good fellowship and a special researcher. As a special researcher, he was invited there. He worked there from 2006 to 2010 and did a very good work there. In 2010, he joined Physical Research Laboratory as a faculty member, and now he is an associate professor in the Space and Atmospheric Science Division of Physical Research Laboratory. He has taken very good initiatives and a very significant contribution he has made to the study of volatile organic compounds, atmospheric emissions, variation of trace gases, and he has used ground-based methods, he has used shipborne method, he has used aircraft observation for this one. He has 60 very good research papers to his credit. He is right now involved in several international projects of NASA, GST, Indian ISRO, and APN, etc. For his work in 2007 in Japan, he was given a certificate of appreciation from the president of JSPS. Similarly, for his as a group award, achievement award, he got from NASA in 2009 for his outstanding accomplishment in the NASA project. While he was in Japan, he was an executive member of the Indian Science Association in Japan called ISAJ. So with these few words, I invite Dr. Sahu to speak to all of us on future challenges in atmospheric measurements. Thank you, and I look forward that you all will ask good questions, and he will answer those questions at the end of the session after his presentation. And okay, welcome.
So, hello everyone, and I am thankful to Professor Vasji for inviting me for this series of lectures that is on sun and climate. Okay. So, I hope you had very nice overview during past 3 lectures about the topic, and of course that's going to be very, very important to understand today's topic. That is the future challenges in atmospheric measurements. As we know that the atmospheric measurements or the observations are the backbone of our understanding of progress happening in the atmospheric sciences in general, and that to climate change. So I'm going to present, of course, it is, you agree with me that it's a very vast topic, and then atmosphere is a huge and a lot of measurements are there. So I will restrict my topic to understand certain aspects, particularly the atmospheric composition, and that too in the lower and mostly in the lower atmosphere, that is in the troposphere. and to some extent in the stratosphere. So once again, I thank Space Education and Research Foundation for inviting me to deliver this talk on sun and planet. So where do we start? We start with the very basic questions. What is there in the atmosphere to measure? Of course, everyone knows that is the atmospheric composition. There is nothing in the atmosphere if you really see that. It's just a mixture of gases. And that too, we know very well, is mostly due to nitrogen and oxygen. Together account for about 99%. Another is 1%. And that other we have argon, significant, carbon dioxide, and trace gases. Trace gases are numerous gases. They are present in a very small amount. Okay. So, but the irony is that about 99% of the researchers across the globe are trying to understand the role of constituents which are just less than 1%. So, why it is so? Why that 1% is significant? That we are trying to understand. Okay. So, to understand the importance of less than 1%, of course, there are many atmospheric processes where the importance can be highlighted, but the best known example is the greenhouse effect. So what you know is greenhouse effect is the trapping of outgoing infrared radiation by certain molecules present in the atmosphere like carbon dioxide, methane, nitrous oxide. And how important these species can be is just you have given the fact. I have given the fact that if you don't consider greenhouse gases, which is much lower than 1%, the temperature of Earth's surface would be about minus 18 degrees Celsius. But with greenhouse gases, the actual temperature is plus 14 degrees Celsius. So if you take the difference, it turns out to be 32 degrees Celsius. And that 32 degrees Celsius is due to greenhouse, mostly we can say it's due to the greenhouse gases present in the atmosphere. So this is one of the effects. There can be several effects where you can highlight the importance of trace constituents in the atmosphere. So it's not, we have to understand the objectives behind the measurement. What is the purpose? It's just not knowing the concentration or composition of the atmosphere, but also we have to understand in a broader perspective, the science perspective related to climate. We have to link measurement with the climate change studies. So, of course, you can learn, people know the connection, but it is always important to revisit the objectives. Okay, there can be many, depending on the studies, depending on the topic, the objectives vary, but we have to see the general objective behind the measurements. So what is the use of atmospheric observation? That question comes in mind. The simple answers are very simple. To understand the processes in the atmosphere. And the processes are two kinds of processes, particularly in the lower atmosphere. That is atmospheric chemistry and dynamics. The next question comes, why is it important to understand these processes? Because these processes in the atmosphere control our environment and play a role in climate change. So one can always ask, once we measure the atmosphere of variables, then why you have to do the continuous measurements? Because the question 3 is about that, and the answer is that atmospheric processes are always changing. And to understand the cause of change and also to predict the future change, we need long-term observation. People call it trends. Okay? So that's the objective of measurements we have. The next question comes, then, I talked about composition, but that's not enough, just knowing the components. So we call it in general variables. What are the variables recommended for the measurements, and that too for the climate change studies? So we have list of parameters like temperature, wind parameter, water vapor, cloud property, lightning, Earth's radiation budget, And of course the composition. The composition in general includes not only the gases but various different kind of particles existing in the atmosphere. And how these variables are measured. You have a lot of platform and techniques: radiation, satellite, and ground-based measurements. Okay. So we are going in details of all these. Okay. So these are the there are, well, of course, nowadays there are innovative ways to measure, but the most widely used platforms are here. Like nowadays, UAV, unmanned aerial vehicle, is being used. Balloon, that is have been very long being used, and that carries the payload in a lower and the middle atmosphere. Satellite band measurements. You have aircraft, you have international space station, you have ground-based remote sensing like radar and lidar, and the ground in situ. In situ here means where the observables are target and the sensor are located at the same place. Okay. So mobile vehicles, and we also study the marine atmosphere, oceanic atmospheres, or that seaborne platform is quite often used. So, but there are challenges in all these. Of course, we have objectives. The objectives gets refined, and then we have challenges, more and more challenges coming, because we want to understand. Because there are a lot of uncertainty in scientific objectives related to climate change, and to solve that to solve those uncertainties, we rely on measurements, more accurate and accurate measurements. So the major challenges are here. If you talk about the atmospheric constituency, global atmospheric constituency, the values can be very low to very high. For example, parts per trillion to parts per million in case of gases, and nanogram to microgram per cubic meter in case of aerosols. So sensitive instrumentation for simultaneous detection of many constituencies is still a big challenge. We can do at a time one or two species, few species. But all species, many species, and measurement together is still a big challenge, and that is with very high accuracy. And many gases like ozone is a very reactive gas, and it is difficult to store a sample there. So we rely on online in situ measurements, but online setups are usually huge and logistically tough to carry and operate them at remote places. We can do in laboratory where facilities are there, or some stations, developed stations where the measurements can be made. Of course, the measurement at network of stations have achieved good progress, and there are still challenges in measurements at global scale. What do you mean by global scale? It's not just integrated column, but vertically resolved measurements. That's going to be very, very important to understand the climate change. So coming back to the the instrumentation part, and I'll go for trace gases and aerosols and clouds. So measurement of trace gases. The most traditional instrument, one of the most traditional instrument is gas chromatograph, and that is in situ measurements. As you know that all species are mixed in air. So we need to separate those species of our interest. You don't want to measure all the species, but you want to measure the species of your interest related to climate change or your studies. Then first thing comes in mind is how to separate those species, and then we use gas chromatograph technique for separation. So that the column inside the GC used to be very, very long, and once the mixed air enters in the column, and then it gets separated according to the time because of different retentivity of different gases inside the column, and then they go to different kind of detector like electron capture detector, time ionization detector, and mass spectrometer. So you get separation of different components or different trace gases according to time, and you get the signal intensity from the different detectors. So different detectors depending on the choice of your species. So you get different peaks, and you integrate, you get, and this signal intensity is directly related to the concentration of the particular gas. But if you see, like many other techniques, so it has disadvantage and advantage. Advantages is that you can measure many compounds. So you change the column and then you can get different set of species. So this can be changed, the column can be changed. But disadvantage is that the time result, the analytical time is quite long, it's 1 hour. So this is not sufficient to observe many short-term processes happening in the atmosphere, because many processes really do happen in a very short time scale. Okay, so that's the disadvantage. So we go to the another type of instrument that is called a spectroscopic analyzer. Okay. So this spectroscopic analyzer, that's again in situ measurements. That means the variable which you look for in the instrument are located at the same place. So there are three main components of this spectroscopic analyzer. We have lamp, we have absorption cell, and we have photodiode as direct. So, for example, in case of ozone, surface ozone, you want to measure, then you have a ultraviolet lamp, and then absorption cell, and then you get, you know, that the air is passing. You don't have to treat the air; it just passes through the cell, and then one cell is without ozone, and then you measure the attenuation of signal, and then that attenuation is proportional to the concentration of the target species in air. So that's very simple technique. Okay. So this technique is very much used for surface measurements, ozone, carbon monoxide, and oxides of nitrogen, sulfur dioxide, etc. So the advantage of this instrument is that it has a good time resolution, but disadvantage is significant. It requires large sample with high concentrations. Okay, and moreover, the species which has a very complex spectral feature or weak spectral feature cannot be detected using like VOCs, etc. They cannot be detected using this spectroscopic analyzer. Okay. Then, of course, the technology has been always evolving. Now we have mass spectrometer, and one of the recent in series is the Proton transfer X mass spectrometer. Why it is being used is that it measures the volatile organic compounds. Many of you may not know, but they are the precursors of ozone. The ground level ozone comes from the photochemical reactions of VOCs. There are too many in air, and precursors of ozone, not only but in the for aerosols as well, in the lower troposphere. Remember, not in the stratosphere. So here is a sample, an example. As an example, this is the measurement of VOCs, volatile organic compounds, in Ahmedabad. Okay. So you see the list of species, numerous, and for complete understanding of atmospheric chemistry, you really have to measure volatile organic compounds. In past, it has been very, very difficult task to measure at very high time resolution and mass resolutions. Now we can, with using this instrument, you can measure even in time resolution of less than 1 second. Simultaneously, not just one species, but all the species can be measured in less than 1 second of time. But what is of course I talked about the advantage of this instrument, but of course I must tell the disadvantage as well. So this instrument is only limited for this kind of species, volatile organic compounds. Another disadvantage is that the affordability, the cost is very, very expensive, and you need a lot of peripherals, so you cannot operate them at logistically difficult places and remote places. You need good everything, you know, a lot of peripherals, you need high power supply, you need cylinders and so many things. So it is very difficult to operate at remote places, but it's a very good instrument. Okay. The next comes is, you know, I'm talking about the gases and our radicals in the atmosphere, and unless we know the concentration of radicals in the atmosphere, we cannot know we don't have understanding about the atmosphere's chemistry to the extent we require for the understanding of regional climate change. In the sense that we know that hydroxyl radical OH is known as the detergent of the atmosphere because it removes many gases, many pollutants from the atmosphere because they are very reactive. So it affects the lifetime in a sense of greenhouse gases also. So if suppose in any environment OH is less, that means lifetime of greenhouse gases will increase, and then we'll have more and more climate change. But the measurement of hydroxyl radical is extremely difficult due to the short atmospheric lifetime, the short of 1 second. So in the past it has been really challenging. But thanks to the innovative technology using the laser spectroscopy, we have an instrument called laser induced fluorescence LIF. It's complex instrumentation which can directly measure the OH concentration. But the earlier measurements were like indirect. You measure VOC and see how VOC is decreasing, and then you infer the OH concentration. But you can now directly measure the OH concentration in the atmosphere. That is the soul of atmospheric chemistry, I would say. The OH radical, hydroxyl radical. Now let's go to the other kind of composition that you must all know is that aerosols, the particles in the atmosphere, and as usual we start with in situ measurement. Okay, so why we measure aerosol and what we measure in the measure of aerosol? So there are two characterizations based on physical properties and other is chemical properties. First thing is to know the concentration in general. Okay, the whole and also there is different kind of the concentration of different aerosols, the bulk as well as chemically separated concentration. So these are popularly known instrument. Accelerometer. This is used for the measurement of very important particle that is called black carbon in the atmosphere, and that plays very significant role in climate change happening in the same time. And it's a filter-based measurement, and the sample is sucked through the filter, and it is deposited. That filter moves to the side where detector is up there, and then the detector and the light is there, light source is there, and you know the attenuation, and that attenuation is related to the concentration of black carbon. That is have been the traditional instrument. But you have now advancement, single particle superconductor, so it can characterize each black carbon particle present in atmosphere. This used to be bulk, but here you have single particle detection using laser. So we are not just interested in just in concentration, but also we want to know the concentration in different size ranges. So you have scanning mobility particle size. So it tells the concentration different size ranges. And not only we know the concentration or size, we have to know the microphysical properties, that how aerosol can act as a cloud condensation nuclei. Okay, so we have CCN counter. Chemical properties, you collect samples using filters, and then the filters are analyzed for different compositions, ionic compositions using ion chromatograph. But this is to be a very cumbersome process, chemically. So what is there? That we have is the particle mass spectrometer. That is one of the greatest, in recent time advancement for aerosol measurement. It is used for the fine mode measurements less than 2.5 micrometers. So here is an instrument which can measure 60 to 600 nanometer particle size and their composition using aerosol mass spectrometer. As mentioned in previous slide, that why need to measure size without chemical measurement composition is because they behave differently in cloud formation and hence climate change. One example is here that how the aerosol lead the emission of aerosol and then the oxidation and then how it interacts with the cloud presence of sunlight. So it gives kind of a cycle or atmospheric role of aerosol particle leading to the climate change. So it's, before going to the new instrumentation or newer technology, we have to always review the what we have before we go to the future. So what we have is for aerosol measurement, we always look for the perfect instrument. What is the perfect? Of course, that changes with time, with the the requirement. But at the moment, it is defined as that the instrument which can measure a lot of masses, and also it can separate depending on the chemical composition. That's called chemical resolution. So we have, some of you may know that these kind of instruments like ECOC, AMS, GC, they have some advantage of measuring high mass, but they have poor chemical resolution. But we have other category of instrument like DCMS, they are good for chemical separation, but they are not done for all masses. So the perfect instrument is which can give you the measurement of all mass as well as chemical separation at molecular level. Okay, so that's the target, and so we are far from the perfect instrument. Okay, so that's the status for aerosol measurement. Okay, so far I talked about the in situ measurement. In situ, again, I'm saying is that the target and the sensor or detector are located at the same place. That's good when you have surface bias measurement, but that's not enough for the climate change. Understanding of climate change, you need to have measurements in the free troposphere, UTLS region, or it's also in the lower troposphere. Okay. So we use remote sensing technique. What is remote sensing? Basically, there are two types of remote sensing. One is active and the other is passive. In case of active, the radiation, the source, is generated within the sensor. In case of passive, radiation comes from external sources, mostly. Okay. So this is widely used. Passive is widely used remote sensing. So what are the components of remote sensing? So you apply it from to hold the instrument. As you know, you have satellite, you can also take remote sensing instrument in aircraft, also you can operate from the ground. What is the target? Of course, since we are talking climate, so in this case, this is our atmosphere. An instrument or sensor, usually it depends. Suppose you are flying in aircraft or it is satellite. So depending on the size and the weight, the detectors are designed. So mostly it is spectroscopic based detectors. Okay, so they measure the spectrum at different wavelengths, and then that is related to the atmospheric variables. So you have the process is simple. You have energy. You have target in case it is atmosphere, it goes back sensor and then processing and then so on, application. So example I am giving here how really it goes into the measurement of trace gases, how remote sensing is used for the measurement of trace gases in the atmosphere. Okay, you have so many gases in the atmosphere, as you can see here. Okay, list of gases. And they have got different spectral features. Okay, absorption at different wavelengths. Here it is wavelength. Okay, mostly you can say that this is visible part and then UV part and infrared part and so on. And they have different bands. Different bands are being used in different satellites. Okay, you have OMI, ozone measuring instrument, TROPOMI, that gives specifically the ozone in the ozone in the troposphere. You have GO, mostly used for the nitrogen compounds, Siamachi. So we have, these are just example, you know, of satellites. We have lot of satellites for the measurements of trace gases. And similarly, you know, the aerosols, lot of, you know, wide spectrum, because they are depending on the site. You know, in case of aerosol, we have site which comes into the picture because the interaction has to happen with that particular wavelength. So aerosols are also like MODIS and Calypso kind of satellites. They are being used, the remote sensing method. Okay. So if you go in detail of satellite remote sensing of aerosols or trace gases, of course, NASA has made significant contribution towards that, of course, and also the European Space Agency. In India, we are also working to develop some instruments are already there, but data is not being really used, but there has been progress. Okay, so at least in proposal front. So we have going into the details of the satellite remote sensing, the three orbits, and these orbits are low Earth orbit, mostly polar orbit, few hundred kilometers from the surface, 700, 600 kilometers. You have geosynchronous orbit and you have geostationary orbit. Okay. So these, which one to use depends on your scientific subjective and measurement objective. Okay. If you want to cover the whole globe, you want to cover the particular region, you want to cover measurement at particular time at particular location. So depending on your, you know, priority and objective, you choose certain orbits. Okay. So we have lot of satellites because, you know, in case of Earth observation atmosphere, we are mostly interested in the global scenario, not in a very localized. So this one is the low Earth orbit with some swathe can cover the entire globe. Okay, so this is very widely used orbit for the atmospheric science studies. Okay. Going to the next example is many of you may know that it's a very important. I mean, this is what is known as A-train satellite constellation. It's NASA satellite. And what is the beauty of this is that they have got 6 in series, same orbit, that is in sun synchronous orbit, and this is for mostly for aerosol measurements. And what is that? The orbit crosses the equator each day at around 1:30 in the afternoon. Okay. So that A-train stands for afternoon. So A-train satellite. So this is being used for the aerosol measurements. Okay. That's the example we have. Okay. Going to the next, I'm almost done with the aerosol and trace gases. What is other composition? Of course, not really the permanent composition, but it's important composition in terms of climate change. Okay, that's the cloud, and that too is particularly important in tropical regions. And that has been challenging. Rather than challenging, it has to be obstacle for the detection of aerosol and the trace gases. But you want to know the obstacle, you want to define the obstacle, not only for the measurement of aerosol or trace gases purpose, but its own purpose. It has its own importance. So what comes in mind in tropical region is that the convection. Convection is a force which takes moisture from surface to the up to the tropopause level. Okay, in less than 1 hour of time. So and then there, you know, so many microphysical processes happen in the atmosphere, and then you need to understand because it, of course, visibly it looks like that, but you don't. But we don't have understanding what is happening inside. Okay. And that's very important to understand the climate change, a role of climate change in cloud form, inside the cloud. Okay. like many aerosols interact, and some gases like ozone also are impacted. The concentration of ozone is influenced by the cloud in the troposphere. Usually, it can go up to the 14 kilometer. Okay, and more importantly, this so it's not just one system. There are many systems coexisting, and the cycle is there. They come up and they die, and on an average, they represent the upward branch of the headley surface. Many of you know this. What is headley? So that's upwelling. So this is the picture we get about the. This is the picture we get, and this is the internal diagnosis of the what the the climate. So the convection system. So what is there inside that? So you have different density of cloud, different kind of cloud, and there is outflow. Okay, so it doesn't just keep going up. It goes to a certain height, and then the dynamics happen to be in horizontal direction. All these informations are really needed in the climate chemistry model. Okay, so how do you get this information? Okay, which instrument gives this information? Okay, so we have very expensive and very heavy satellite payloads. It gives about the rain and the cloud. We have Circle Rain TRMM satellite. It's from NASA, and it was designed to understand the variability of precipitation within the tropics originally, which is, and you know that the climate change impact the water cycle, and then again further it goes kind of feedback mechanism, and again changes the climate system. Okay, that's very important outcome of the climate change. The change in rainfall pattern, so that we need to detect. We rely on network of ground-based stations for the rainfall detection, but we have satellites, so we can also have rainfall data over the not only over the land but also over the the, the ocean. But that's one thing. That's not the topic of my today's presentation in real sense, but this is more relevant. The cloud state, cloud profiling radar. So that's the picture. If you go to previous slide, this picture has come from this kind of satellite, cloud, the instrumentation, cloud profiling radar, what's called CPR. So this is another looking, and then it gives the echo, the measures echo of cloud at different heights. So echo is kind of given in this scale. It's in dB units, but not precisely defined here. Sorry. So that kind of information we are getting from the cloud profiling radar. Okay. So that's very important to understand not only the chemistry but also the dynamics and the tropical atmosphere. So so these are all in addition to campaign-based studies, some observation, annual observation, and so on, we should have long-term observation. And that has been one of the major focus of WM. Okay, they have come with several stations where they are focusing on long-term observations. And long-term observations are not possible because in many platforms like aircraft or satellite has of course decadal scale, but you want more long term, then the satellites has its own lifetimes. You cannot continue measuring same the way you can continue at the ground. So most of the long term observations are based on ground based observation, or at the most balloon based observations. Okay, so what are those? You have big instruments, in situ instruments. You have radio sounds, you have LiDAR, radar, microwave, infrared, radiometer. You measure the intensity of sunlight at different wavelengths, and you have wind profiler. This kind of new technique coming up. This gives the measurements, particularly in the troposphere, the winds. Okay, but that's so these are the instruments or platforms. I would say the platforms used for the long-term measurements. So we are heading towards the end of presentation, but more or less I talk about the status or the challenges. It's always important that what we have learned from the atmospheric observation so far. Okay, and one of the most important measurement that long-term observation of carbon dioxide. You know the carbon dioxide, the agent of climate change, best known, most popularly known. Of course, there are many agents, but CO2 has been regarded as because it comes from the fossil fuel, and then that the use have been ever increasing, and then the imprints can be seen here. That in Mauna Loa Observatory, the measurement is started in late 50s, and then you have long-term measurements up till now, and it's still continuing, and we see the ever increasing concentration. So Mauna Loa is far from the direct emission sources, and then this represents the globally well mixed carbon concentration of carbon dioxide, and that is well established. Once CO2 is there in the atmosphere, definitely it will affect the greenhouse process, and definitely it will cause the radiative imbalance, and the radiative imbalance we know is the climate change. So that is well established. So this is a very obvious example how the observation can change or improve our understanding about the climate change. The next is another landmark observation is that we were at risk because of extensive use of chlorofluorocarbon. Earlier it was thought to be a wonderful compound, CFCs, because it is not so reactive. It is just kind of a very inert gas, and it has no harmful impact on the local environment. And that's true. It doesn't harm anything in the lower atmosphere. But nobody had predicted at that time that it can impact some other part of the atmosphere, that's the stratospheric ozone. And discovery has been possible not using theory, only through the observation. So these are the 3 British scientists from British Antarctic Surveys, and they reported in Nature paper in 1985. This Jeff Foreman, Gardiner, and Sanklin, about the extensive ozone loss in spring over the southern pole, and that too was possible using the Dobson ozone spectrum. That tells the importance of measurement. So if you don't have observation, you will. So observations are not done just done to understand the problem known, but the regular observation can bring some surprises as well. So you don't have to be very clear in objectives, but if you have observations, then of course analyze the data, and then you can get something new. So that's the beauty of the products. So the big campaigns, you come to the regional things. So it's not only just about the global things, but also you know about the Indo-X campaign. So there was kind of haze observed over the Indian Ocean, and that haze was the cause, and nature of haze was studied using extensive campaigns, deploying all sorts of platforms, ground, remote sensing, aircraft, and so many satellites. Okay, and they could study the haze. As they moved away from the land, they said, the haze gets thinner and thinner, so this close to land, and then you put it more, and then far over the Indian Ocean. So this kind of understanding we get only from the big campaigns. Big campaigns means you deploy a lot of instruments, different kind of instrument covering the different parts of the atmosphere. Similarly, I was a part of the Arctis campaign, and the objective was to understand the the role of what you call Arctic haze, then in the local warming. So ice is, you know, the ice coverage is receding over the northern pole, and then they wanted to understand, people want, it's part of climate change, what is there. So we had, you know, extensive measurement of more than about 400 components, atmospheric components, using all possible platforms over the polar region. Okay. So last slide, the future. Okay, we need everything basically, whatever we have been using, we have to deploy our instrument and operate in all possible manner to collaborate with not only the instrument people, but also with the modelers. Okay, they get important feedback, because ultimately the just observation doesn't give, the just measurements are not enough to understand the climate science. All the information goes into the model. Okay, the processes which you know from this observation is through the model only, because the atmosphere is a complex system, non-linear system. So you cannot just translate your observation to a climate science. It has to go through the model. Okay, so we need to really work with model or better and better understand. Okay, so once again, that's the end of my presentation, and I thank you all for your attendance here, and then we'll see if you have some important questions. Thank you all. So, okay, we have that. We've got some questions, and then so we have one question about what is proton transfer reaction, and that is proton transfer reaction is that this is one of the ways to ionize. You know, in mass spectrometer, you first thing what you do is that you ionize the molecule, the species, and usually it is using bombardment with like electron impact ionization. But that if you use that, then the identity will be not there, because it will fragment. So we do not know the species identity will be lost. This is a soft ionization. That means it is, the molecules are ionized just by exchange of proton. So VOC is volatile organic compounds takes one hydrogen and get ionization itself, and there is not much fragmentation. So it remains. So identity is kind of intact. It is not changed. It is not changed. Okay. So that way it is important. So it is kind of, and the ion which is the hydronium ion. So hydronium ion react with VOC, and it gives one H plus one proton to the VOC. So that's the question. I mean, but that the question is how in situ measurement detect all the gas at the same time. The questions, this question is, of course, as I said, that perfect instrument cannot detect all these species at the same time. Okay. So, but in situ measurements, it used, why you say in situ is that you can in situ measurement technology, you can make your instrument as complex as possible. In that sense, we can say we can do measurements of many species. But if you are using some other platform, remote sensing platform, your choice is already limited. You have to rely on the radiation, spectroscopic, mostly spectral analysis, and also the size and the weight of the instrument comes in. So in that sense, so yeah, I didn't mean to say that all gases, but many gases, more and more gases is possible using in situ measurements. I have never come across permanent call that about black carbon. I have that is I don't think we have measurements of black carbon using satellite. Okay, so it's still not there. So yeah, yes, ISRO had, that's what we have. Of course, ISRO PR, these are all in proposal levels. I was a part of a committee where we framed the requirement by the scientist, and then we had discussion in ISRO headquarters about the, the, the possibility of measurements using satellite. So it's ongoing proposal. So in near future, yes, there will be. I'm very much sure about that. So cumulonimbus cloud, that is basically it is related to the convective clouds, kind of clouds which you get mostly in the tropics, and that genesis is through the convection. That is Kasibat's answer what is meant by cumulonimbus cloud. Yeah, I'm not much, because one of the things is not just Neil. I'm trying to answer. You're right. How our part of satellite phonics were used for remote observations. That's that I don't have much information about that. But what is the problem coming is about the use of the data using the satellite borne observations, even doesn't matter whether it's or some other agencies, as validation. We have data, but those data are not validated, and there is a difficulty or a lot of uncertainty to use it for scientific purpose. Okay. That is another challenge. That is not, of course, related to the observational measurement, but the retrieval of data is very important. That needs a lot of work. So many data are just not being used because they are not validated or not retrieved the way it should have been. So that's the problem. IMD measurement of the IR images of volcanic information. No, I think the image from the IR images we gauge mostly it is IR images about the water vapor, and then not much about the gases. That's a good answer. Yes, Neil Vadoria, you are talking about, you're asking about CO2. That's you're right in a sense. That's reflect the seasonal change, that the variation within a year, the variation which you see in the CO2 plot. Yes. Is there a recovery of ozone in a, yes, there has been, the use of CFCs have been banned, and then we are on recovery mode. So, but it will take time. Okay. Why only polar parts have ozone hole? Okay, that's very interesting question, but I don't think I will be able to answer. But I know the answer, but it will take time, in a sense that you need to understand not only the chemistry but the dynamics also. So I can just say that there is a specific kind of cloud, what is called polar stratospheric cloud. That's there in the polar region, and that too particularly high in the southern pole. And that is the platform where a lot of heterogeneous chemical processes happen and release a lot of chlorine radical in a plume when sunlight comes in spring, and that catalytically kills ozone. That's why the cause of ozone hole in the in the in the polar region. Okay, that's the so Srin has asked same question about the. So that cloud is not there in other part of globe. So that's the one of the reasons for the ozone hole. What is the effect of Antarctic ocean by ozone layers depletion? Of course, the very simple thing is that the radiation imbalance. A lot of ultraviolet will penetrate to the lower atmosphere, even to the marine levels, and a lot of sensitive, species are there in the ocean water or nearby. Even then, they may not be able to. We don't have that much, but the risk is there. The exact nature, of course, if the harmful radiation, it can damage the cell, and then the disease can come across. So in long run, the exposure of rays are not so harmful, but once ozone is there, which is there for at least, it has been there for more than 34 years, and it will be there for more 34 years. So that's long exposure time. So there is a risk. So where the exact nature is of risk is very difficult to spell out. Yes, observations are mostly there in big cities, as you know, in particularly, but also we have a lot of observatories coming up at remote places. Like WMO have set up observatory at remote places. GAW, that Global Atmospheric Watch Program. So they have set up, and also, not only we go to the stations, but also we operate our instrument in campaign mode. So where we go in remote places, not only over the ocean but also over the land. I agree with Vijay Agrawal that main outcome of Windows were the serious sulfur-based cloud on west coast of India, bringing radiative cooling, and I have to see the sulfur-based. What do you mean by sulfur-based cloud? But this has been your second point is really one of the major outcomes of the program, the radiative forcing in the mesotroposphere. We have. Is there any method to predict precipitation using spectroscopic in situ measurements? No, hardly. The precipitation, not really, but the cloud has been possible. The measurement of cloud, that precipitating cloud has been possible, but not exactly the precipitation. About the sorry. Ajay Kumar Mittal, ozone depletion concentration polar ends due to environmental problems? No, not really. The cause has been the CFCs, and it is scientifically well established. Okay, the angular momentum part could be related to dynamics happening, and that can go into ozone hole. I am not sure about that, but not really the direct impact of angular momentum. So I think I have come to the almost answered all the questions, and I have a couple of minutes to go. If you can quickly type, I'm not sure, but of course you can always keep me. If I have not answered you satisfactorily, then you can always write me an email, and much appropriate or proper answer, because I have to answer so many. I don't have much time. So once again, I end my presentation here, and thank you all for your kind attention, and I hope you'll you'll come with some questions, and you'll you'll be interested in atmospheric and climate science. Thank you.
Yes.